3.6. I think you're all familiar with the formulas of compounds. We traditionally don't always write names of compounds. Sometimes to shorten things up, we write formulas. So, for instance, instead of saying carbon dioxide, we call it CO2. Let's look at the different types of formulas that we have. The first and simplest type of formula that a compound can be designated with is called an empirical formula. I've got an example here, CH. This is the simplest whole number ratio of the elements that are involved in the particular compound. The second type of formula, a formula that gives us more information, is known as the molecular formula. This is just simply the empirical formula times some integer. So in this case, I've got the empirical formula times n being that subscript on the far right. If we know what n is and we know what the empirical formula is, then we'll know what the molecular formula is. And here's an example of that. C6H6, more formally known as benzene. C6H6 would be the molecular formula. CH would be the empirical formula. So in the case on the board with the benzene, the actual formula for benzene is C6H6. The actual formula for benzene is the molecular formula. So when do we use empirical formulas if they're not the actual formulas? Well, if you remember back to ionic compounds, let's take a look at magnesium oxide, which magnesium has a 2+ charge and oxygen has a 2- charge, and if we crisscross those, they reduce out. Empirical formulas are crucial to use when we have substances like magnesium oxide, which are ionic compounds. Because if you'll remember, ionic compounds are just ratios of the elements involved. So if we think about magnesium oxide, it's not just one magnesium atom and one oxygen atom. It's a billion magnesiums and a billion oxygens, all alternating in some form of crystalline fashion. Covalent compounds are different. We know that covalent compounds are molecules unto themselves. So they need molecular formulas. C6H6 is very specific. It says there's exactly 6 carbons and 6 hydrogens in that one molecule, and that one molecule acts on itself. So ionic compounds only have moleculars. So ionic compounds have no molecular formulas, no MF. Okay, no molecular formulas. Let's try an exercise with this idea. We've got something called adipic acid. And we know that adipic acid has 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen by mass. And then we get a molar mass of the compound. And in a second, we'll talk about where these percentages come from and how we know these percentages. My question may be to you is, develop the empirical formula for adipic acid. So let's do that now. So we know that we got 49.3% carbon, 6.9% hydrogen, and 43.8%. Sorry about that. I'm going to treat every single one of those as, instead of percentages, grams. I'm going to say, okay, I've got a 100-gram sample. Well, how many grams of that is carbon? In this case, that's 49.3 grams. 49.3 grams of carbon. Okay, and then I've got 6.9 grams of hydrogen. And I've got 43.8 grams of oxygen. Now, when we're writing molecular and empirical formulas, grams does not help us out. Because formulas, or compounds more specifically, don't react in grams, 10 grams of this stuff to 1 gram of this stuff. Instead, they react by the number of particles. So a certain amount of carbon atoms and a certain amount of hydrogen atoms come together to form a compound. Well, we don't want to work on individual particle levels, so that's where the mole comes and helps us out. So what we're going to do to each one of these guys is take the molar mass of the respected, of the compound, or of the element, and we're going to turn the mass into moles. Carbon's molar mass is 12.01, so I'm going to put that here on the bottom of my unit analysis in 1 mole, so that the grams cancel out. Grams gone, grams gone. Hydrogen is 1.01, put that on the bottom for 1 mole. Mole up there. Grams gone, grams gone. And oxygen is 16.00 grams over 1 mole. Again, grams gone, grams gone. All right, let's do the calculation of all 3 of these. 49.3 divided by 12.01 is going to give us about 4.10 That's moles. 6.9 divided by 1.01 is going to give us 6.83. Again, that's moles. Okay, and 43.8 divided by 16 is going to give us 2.74. And what we're going to do now is look for a ratio of the carbon to hydrogen to oxygen. So your next step is to divide each one of these numbers, 4.10, 6.83, and 2.74, by the smallest number of them, of that set. Well, in this case, that's 2.74. So every number here gets divided by 2.74. 2.74. And this gives us a ratio of the elements involved in the compound. Okay, and I'm going to do those calculations down here. So for carbon now, 4.10 divided by 2.74 equals 1.5 roughly. And you'll see down here, I'm really not keeping track of sig figs, and that's okay. You'll see why in a second. 6.83 divided by 2.74. That equals about 2.5, so hydrogen equals 2.5. Okay, and then oxygen, we'll go over here. Oxygen is 2.74 divided by 2.74. I don't need a calculator for that. I know that that's 1. All right, so let's see what I can do with those numbers now. I'm going to just erase this top stuff. Keep the bottom stuff with me. When you're writing a covalent compound, specifically one that has carbon, hydrogen, and something else in it, it's always convenient, or it's always correct to write the carbon first, followed by the hydrogen, followed by everything else. Oxygen being, in this case, everything else. So right now what we're saying is that for this empirical formula we have 1.5 atoms of carbon for every 2.5 atoms of hydrogen for every 1 atom of oxygen. Now hopefully at this point you're saying, hold your horses. That can't happen because we can't have half an atom of carbon. And you'd be correct in saying that. So what would we have to do to this entire thing to get rid of those halves? Well, can we simply multiply it by 2? Sure, we can do it. I want to warn you, this 2 is not the n, not the integer n that we had on the first slide. We are just trying to get these numbers, these subscripts, as whole numbers. And when we do that, we'll find that the empirical formula for this compound is C3H5O2. All right. So let's go back to our slides then. Let's see if we were right here. C3H5O2. Great, awesome. Now here's the next question. What is the molecular formula? Well, for the molecular formula, we're going to need that number 146 grams per mole, or the molar mass. So let's go back to our drawing that we were doing. Okay, and I'm going to go ahead and erase the bottom of my slide here. All right. My molecular formula is a my molar mass in total is 146 grams per mole. Well, let's do something. Let's find the molar mass of this guy. So I'm going to say, well, what's the question mark molar mass of C3H5O2? Well, if I have 3 carbons, that's 12.01 times 3. And if I have 5 hydrogens, that's 5 times 1.01. And if I have 2 oxygens, that's 2 times 16. And I get a total of 73.08. So this equals 73.08. I'm going to try to fit it in here, grams per mole. All right? Now let's think. What was our total molar mass? Our molar mass was 146. Okay, remember that was the molar mass of the molecular formula. The molar mass of our empirical formula is 73. So my question is, how many 73s can I fit into 146? I bet you're all pretty good at math. It's going to be 2, right? It's going to be very close to 2. This number right here, ding, 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 this is that n that we talked about on the first slide. This is the n integer. That equals n. So my molecular formula, if my empirical formula was C3H5O2, I'm going to multiply all of that by 2 and that'll give me my molecular formula, which in this case is C6H10O4. C6H10O4. That's my true compound right there. Let's go see if we did that right. C6H10O4. Awesome. We got it. We got it. All right, so I got a test question for you. See if you can do this on your own. First of all, let's look at how we get these numbers, by the way. To find empirical formulas experimentally, we use a tool like the furnace shown above. Your sample for this tool is placed inside of a little furnace here. And we put some oxygen in. There's the oxygen. And we heat that sample up and it burns. And if that sample is made out of carbon, if it's made out of hydrogen, well, we know that carbon dioxide and water are going to be two of the products given off. We have a water absorber. We have a carbon dioxide absorber. And then all those other gases kind of leave the system. So we know how much water is absorbed, and we know how much carbon dioxide is absorbed. If we know how much oxygen went in as well, we should be able to figure out how much hydrogen and how much carbon were in our original sample. Right there. And that's how the furnace works. Okay? So here's your test question. Let's see if you can get this one. It's a tricky one. Let's say that my sample is 0.1156 grams in total mass, and I put that in the furnace. And 0.1638 grams of CO2 and 0.1676 grams of water are collected. I want to see if you're wise enough to determine the empirical formula of the substance, if it is known to contain carbon, hydrogen, and nitrogen. All right, let's figure that out. All right, that's it.